The Queen Mary 2 is a city at sea. She's the largest and most expensive ocean liner ever conceived. Stood on her end, she's taller than the Eiffel Tower, and her engines are large enough to power Southampton. She is capable of crossing the roughest seas on the planet, while her passengers enjoy unrivaled luxury. She is unique among ships.
It's everything about her. It's her strength, her speed, the majesty of the ship itself.
In an age when ocean liners have almost disappeared, she is a vessel that few believed would ever be built. But to construct this 21st century icon, the engineers had to do nothing less than reinvent shipbuilding. April 2007, the world's largest ocean liner, the QM2, was at her berth in Southampton, preparing for her weekly transatlantic voyage to New York. She's only at port for 11 hours. All around her is mayhem. At sea, she earns £30,000 an hour, so a quick turnaround is essential. This is a ship that never sleeps.
We arrive around 7 o'clock in the morning, discharge up to 2,700 passengers, embark the same number again, and sail again by 6 o'clock that evening.
She must take on 3 million litres of fuel, enough to drive a car to the moon and back 70 times. That's a bill of over £500,000.
Starboard pod, 2 to starboard.
Starboard pod, 2 to starboard.
The Queen Mary 2 set off on her transatlantic voyage, a 3,000-mile journey from Europe to America. This stretch of water once provided a thriving commercial passenger business. Until the 1950s, the only way to travel across the Atlantic was on board an ocean liner. The ship company, Cunard, had a reputation for some of the finest ships. The Lusitania, Queen Elizabeth, Mauretania, and the original Queen Mary ruled the waves. Then, one autumn day in 1958, a fatal blow struck the ocean liner industry, the first commercial transatlantic passenger flight. In a stroke, the journey time was cut from 5 days to 15 hours. 40 years later, and the only ocean liner still doing this crossing was the QE2. Her age was beginning to show, and the once proud Cunard was in deep financial trouble. It looked like the golden age of ocean liners was over forever.
If you'd asked me in 1998 whether there'd be another transatlantic liner after the Queen Elizabeth II, I would have said categorically no.
No one could see a future for this slow but stately form of travel. No one except one billionaire with a vision. Mickey Arison owns Florida's Miami Heat basketball team. He also chairs Carnival Cruises with annual revenue of £6 billion.
I saw a television special on what was called the last superliner, QE2, and I remember being very upset by that.
He and his family have a very personal attachment to ocean liners.
I sailed on the Mauretania in 1954 when we immigrated to the United States.
The Mauretania was one of Cunard's classic liners.
I can remember being at the west side of Manhattan and being fascinated by that line of ocean liners that used to dock on the west side of Manhattan.
By the 1990s, the public were choosing different ways to travel and spend their holidays. Ocean liners were a distant memory. But in 1997, Mickey Arison detected a shift in mood.
The movie Titanic had come out, and there was a kind of a nice nostalgic feeling about that movie and about transatlantic crossings. That feeling of nostalgia gave me the sense that if we could bring back that feeling of the great transatlantic voyages of the past, that we would have something special.
And he was prepared to stake his wealth on it. Arison bought the failing Cunard with the intention of building the first new ocean liner for 30 years, the Queen Mary 2. At a cost of £500 million, Mickey knew that she would be the most expensive ocean liner ever constructed. And time was against him. To keep the tradition alive, the QM2 had to be ready to take up the baton when the last remaining ship, the QE2, laid it down in 2004. Her sheer scale would present one of the greatest engineering challenges in maritime history. She would be the tallest, broadest, and longest passenger ship of all time. Mickey needed a remarkable naval architect to design her. Stephen Payne, senior naval architect, is as passionate about ocean liners as Mickey. When he was 10, Payne's parents took him to visit the newly completed QE2.
As a family, we walked around that great ship for 2 or 3 hours. Really fired my imagination, and I really felt, oh, wouldn't it be great one day to be able to design and build ships such as this?
Payne agreed to take on the QM2. His dream job would test him to the limit. Over a 2-year period, he and his team would have to produce a phenomenal 80,000 design drawings, from the shape of the funnel to the position of the propellers.
I really did sort of eat, sleep, dream, everything Queen Mary 2. It was such a mind-blowing, mind-boggling project to be involved in.
Next, Mickey had to find a shipyard with the experience, space, and ambition to build Payne's iconic design. One place stood out: the French Chantier de l'Atlantique, the shipyard of the Atlantic. It had the perfect pedigree, the birthplace of 2 legendary ocean liners, the France and the Normandy. Since 1962, the crew of 3,000 shipbuilders had been making holiday cruise ships. These are more like hotels at sea and not capable of crossing rough oceans at speed. So they leapt at the chance to build a true ocean liner again. They had no time to lose. January 16th, 2002, construction began with the first of 300,000 pieces of precision-cut steel. 900 miles of welding and over 10 million rivets would combine to form a ship 3 times the size of the Titanic. The shipyard's chief designer was under pressure.
Delivering the Queen Mary 2 behind schedule would have been a disaster for the shipyard.
Mickey Arison demanded that the ship must be completed within 2 years, an incredibly tight deadline. The Chantier team couldn't afford to relax. Every day the shipyard ran over would cost £300,000. July 4th, 2002, the first momentous stage in the construction of the Queen Mary 2 was reached, the keel laying.
Current master of the Queen Elizabeth...
The man who will captain the QM2 presided over the ceremony. After 7 years in charge of the QE2, Warwick's not short on ocean liner experience, and even he was in awe of the megastructure under construction.
I have to say I was totally overwhelmed. I never thought there would be another Atlantic liner, but when I heard that it was going to be a much bigger one, I was in awe of the whole project.
British and French coins were placed inside the keel to give the ship and her passengers luck. The construction team could now join the first steel blocks together. The unmistakable shape of a classic liner began to reveal itself. The cost of building the largest and most luxurious ocean liner on Earth is phenomenal, 4 times the budget for the film Titanic. Success hinged on the finished ship producing enough money to be profitable.
You're not going to make a nearly billion-dollar investment unless you can get a return on your investment.
That came down to one thing: space. The ship had to be big enough to carry more fare-paying passengers than any other liner in history. And to draw the crowds away from the transatlantic planes, she had to be bursting with every distraction imaginable.
They want first-class spas, they want variety of food and beverage outlets. They want all the amenities of a first-class resort.
Which created a problem. The maximum size of the ship's design was limited by the dimensions of 3 passages she would sail through. She could be no higher than the Verrazano Narrows Bridge in New York, no longer than the turning area near Southampton, and no wider than the Panama Canal.
As close as you can imagine.
Owner Mickey Arison then raised the bar even higher. He insisted over half his passengers had to have their own private balcony space.
I can remember the first meeting I had with the naval architects when they told me that on a transatlantic liner you can't have any balcony cabins. And my answer was, if we can't have any balcony cabins, we can't have a transatlantic liner. And they said, okay, we'll go back to the drawing board.
To create enough space despite the 3 design constraints, Stephen Payne had to rewrite the rules of shipbuilding.
Every time I met Mickey Arison, he would ask me, how many more balcony cabins have you managed to squeeze into the design of the ship?
Payne experimented with increasing the ship's height to fit in enough cabins and balconies. But this made the ship dangerously unstable. For every ton of weight on top, there must be 2 tons below to balance it out. Her sister ship, the QE2, gets around this problem by using aluminium, which is lighter than steel. But this is no longer an option. After 30 years, aluminium suffers metal fatigue, and the QE2 now needs frequent repairs. Payne's design had to last longer. The challenge was so great, the project nearly collapsed.
Twice we were put on hold because the economics of building the ship just didn't seem to work.
But Mickey insisted a solution be found. Eventually, Payne and his team cracked the problem. They proposed to build a ship that's longer and wider than ever before to accommodate enough passengers. This enormous stable base meant they could increase the height and still use steel for the structure. But her beam had to be far wider than planned, breaking the initial ground rules.
The ship had to be large enough to meet the demands of our guests, and clearly could not be built to go through the Panama Canal.
This decision came at a heavy price. During yearly round-the-world voyages, the QM2 would be forced to travel via South America instead, a 9,000-mile voyage, which takes her round Cape Horn, one of the most dangerous passages on the planet. But Mickey got his balconies. The QM2 must round Cape Horn during special voyages, but most weeks she must tackle another ferocious force of nature: the Atlantic Ocean. Rogue waves in the Atlantic have long been a staple of mariners' tales, but cutting-edge science has recently proved they are more than just myth. Oceanographer Simon Boxall has been studying these dangerous waves for years.
Rogue waves are more than capable of sending a ship to the seafloor in a matter of just minutes.
Certain combinations of wind and swell do produce dangerous waves. When the wind and current come from opposite directions, waves can become as tall as 3-story buildings.
In our tank, we have 2 storms. We have Storm Emily in the North Atlantic, and we have Storm Emma in the South Atlantic. And they're going to create waves that will come together somewhere in the middle of the Atlantic. And if we start off and ask Storm Emily to create some waves, we can see that the waves come to about there on the scale of our tank. That's about 10 or 15 metres. If we now ask Storm Emma to come into action, we can see those storm waves meet in the middle, and our storm waves suddenly go from 10 or 15 metres to almost over the top. And that is over twice the height of our original wave, over 30 metres. And that's what we call a rogue wave.
Outside the laboratory, on the Atlantic Ocean, these waves are a terrifying threat. In 1966, an Italian liner, Michelangelo, was hit by a 25-metre wave on its way to New York. The wave ripped open the first-class cabins beneath the bridge and killed 3 people inside. 50 more were injured.
That event really crystallised my thoughts into making this ship as safe and as strong as possible.
By the end of the 20th century, wave heights had increased by an average of 20%, possibly due to climate change causing more powerful hurricanes.
What we're finding is because there's more heat energy in the system, these waves are getting even bigger and more frequent.
Stephen Payne had to create a hull that could withstand an onslaught from the sea. He knew the life of everyone who sails on the Queen Mary 2 would depend on his design. He planned 3 groundbreaking elements. The thickest ever hull on a passenger ship, 50% more than standard. The workers would be retrained to weld these steel plates over an inch thick. A radically shaped bow with a protective flare to divert the oncoming waves. And, as a last defense, a huge breakwater barrier on the foredeck. Any water that makes it onto the deck would be redirected back into the sea before it tears a hole in the side of the ship.
That really does shout out to the Atlantic, I'm coming, get out of my way.
Payne's wave-beating design looked impressive on paper and in the shipyard. But the design had to pass crucial tank tests. She must be able to handle the roughest seas without compromising her speed. But this hull shape had never been used before, so no one knew for sure what would happen. Holland has the world's largest marine testing tank. It measures nearly 200 meters long by 45 wide and 5 deep, the equivalent of 14 Olympic swimming pools. A 12-meter-long model of the QM2 would test whether the ship could survive the North Atlantic. Guillaume Gaillard was in charge of testing her seafaring ability.
You're making sure that you won't have any bad surprise at the moment the ship is delivered.
First, industrial wave machines simulated hurricane conditions.
Stephen Payne really insisted they wanted absolutely to see how the ship would handle the most extreme weather. So of course it's not nice sailing conditions, not pleasant.
The first test began. Huge waves were deflected to the side of the model's flared bow. The breakwater rapidly disposed of any water that made it onto the foredeck. Payne's new protective hull appeared to work perfectly. Every aspect of this new ship tested the design team. One of the most fundamental challenges was generating enough power. The engines must supply electricity for a community of 4,000 people. This must power the lifts, lighting, air conditioning, water treatment, and everything required for the ultimate in luxury. And that's not all. Huge power is needed to propel the ship across the Atlantic.
On the Queen Mary 2, this is the biggest propulsion system ever to be made.
To reach speeds necessary for the 6-day timetable, keeping the company in business, the ship must produce the energy equivalent to powering 200,000 homes. That's a city the size of Southampton.
Speed of the ship is absolutely fundamental, and it was of crucial importance to ensure that the ship would be able to arrive and depart on schedule.
4 giant diesel engines were placed deep in the bowels of the ship for stability. Their size meant they couldn't be fitted into the completed ship. Instead, the ship had to be built around them. The pistons are nearly half a metre across and have a capacity 80 times bigger than that of a double-decker bus engine. Each engine boasts 16 of them, and at full throttle pumps out 17 megawatts of electricity. This pushes the propulsion system to 24 knots, as fast as most holiday cruise ships. But unlike cruise ships that are designed for relaxation, the QM2 must be an efficient mode of transport, capable of achieving nearer 30 knots. Payne needed to find a way of generating much more energy. He came up with an innovative idea. He added a pair of smaller gas turbines, like those on a Boeing 747, which generate huge power on demand, 50% more than the diesel engines. But there was a knock-on effect.
Gas turbines produce a lot of power for their size, but the biggest problem that they have is that they need an enormous amount of air.
Drawing this air all the way down to the turbines in the engine room through large ducts would take up valuable space. So the designers defied convention and came up with another idea.
Eventually, a very simple and elegant solution was found in that the gas turbines were placed up immediately behind the funnel, where they had full access to the outside air.
The turbines are extremely light because they're designed to fly, so putting them at the top of the ship wouldn't affect the stability.
And that's how the problem was solved.
October 2002. With the diesel engines installed, the rest of the ship could now be built around them. With less than 14 months to go before the deadline, the shipyard had to work out how they could build a ship twice the size of the QM2's predecessor in half the time. They opted for a technique never used on an ocean liner before. First, they divided the entire ship into 98 blocks. Each block was built separately, with the raw steel being welded into shape in huge workshops. The pre-assembled blocks were then fitted together. One by one, each of these giant sections, weighing up to 600 tons, was lowered into place. They had to be pinpoint accurate. With the sections centimeters away from each other, powerful hydraulic pull jacks held the blocks in place. The team checked the fit, then welded the section to the growing vessel. It was like putting together a huge 3D jigsaw puzzle. Back at the testing tank, the model ship faced its next trial. In calm water, it had to reach the equivalent speed of nearly 30 knots. Early results were dire.
First test showed that the shipyard would have very, very difficult time in actually achieving the contract speed.
The ship had to be able to cross the Atlantic in 6 days, or Mickey Arrison's new venture could hit the rocks. Somehow, the QM2 had to go faster. The shipyard had to increase the speed of the Queen Mary 2 to fulfill their contract. The pressure was on engineer Henk Valkhoff.
we really had a big problem. And I think people from QNet were expressing their concern also here and saying, well, this has to be solved.
The simplest solution would have been to increase the power, but the propulsion system was already under construction and could not be changed.
We gave the shipyard a very, very tight limit on the amount of power they could use to drive the ship to the speed we wanted.
They would have to find another way. Henk Valkhoff turned his attention instead to the bow. As ships move forward, water is forced into a bow wave at the front, which causes drag.
Here we see a traditional bow. There's a lot of waves and turbulence on front of it, and that's slowing down the speed of such a ship.
Many modern ships, including the QM2, incorporate what's called a bulbous bow to counteract this effect. Water flows up over the bulb. Then, as it comes back down, the two flows of water partially cancel each other out, reducing the bow wave.
When I look at the bulbous bow, like on the Queen Mary 2, you see a significant reduction of drag, improving the speed.
But even with a bulbous bow, the QM2 model was not fast enough. In a bold move, Valkhoff increased the size of the bulbous bow by nearly 2 meters for maximum effect, making it, at 12 meters, the longest bulb on any passenger ship. The model finally hit its target speed.
We have seen performance improvements up to 15 to 20%. So this ship is so fast, I cannot keep up with it.
The shipyard engineers were back on track. But it wasn't plain sailing yet. No one would want to pay up to £20,000 per cabin to cross the Atlantic in a ship that's so unstable it makes them feel seasick.
On a cargo vessel, all the cargo is secured. On a passenger ship, we don't tie the passengers down.
Stephen Payne had a better solution. He planned to use well-established technology, but on a large scale. He added 2 pairs of huge stabilizing fins, each with a surface area of over 15 square meters. In calm weather, to reduce the drag, the stabilizers are housed inside the ship's hull. In rough weather, they're deployed at the push of a button to counteract the pitch and roll of heavy seas. The 70-ton fins extend in just 30 seconds to a distance of 6 meters beyond the ship's side. Here they move through the water like the wings of a plane. The new stabilizers will cut roll by 90% and make the QM2 twice as stable as any previous ocean liner. Back at the shipyard, the final block was ready to be fitted. The iconic black and red Cunard funnel. This is like a badge of honor among ocean liners. But at the design office, it was causing a real headache. The purpose of a funnel is to lift the engine exhaust above the passengers on deck. But when Payne calculated the height of a standard funnel, he realized that it will collide with New York's Verrazano Bridge.
Getting under the bridge was a real problem. And in fact, some of my colleagues said that if I got my calculations wrong, it would only be a problem the first time.
If he simply shortened the funnel, smoke would envelop the passengers, ruining for many the trip of a lifetime. The designers had to go back to basics. Using a model of the funnel, they experimented with the aerodynamics at the top of the ship. They added curved surfaces to the base of the funnel and used a wind tunnel to replicate air moving over the ship. The wind indicator showed that air would be forced up by the curved surfaces. This flow of air would push the smoke from the funnel high above the passengers on deck. With the extra boost from these huge new wind scoops, Payne could now confidently shorten the funnel to sail under the bridge. With the top of the ship in place, Stephen Payne now turned his attention to its base and the thorny issue of manoeuvrability.
Yeah, because there's different standards between passenger and crew.
Commodore Warwick knew that he'd need to control the ship's movements very precisely, especially on the Solent, a stretch of water near Southampton.
Solent is a very tight channel for a ship this size, so it's essential that we get the manoeuvrability of the ship exactly right to accomplish these turns.
Payne had heard about a recent breakthrough in marine propulsion, known as pods. These cutting-edge devices are used to power the newest holiday cruise ships. They're so effective, they can turn a ship within its own length. But there's a downside. This high-tech machinery had never been used on a ship of this scale. They would be fitting untested technology.
We had to be very, very careful to ensure that by putting 4 pods on the ship, we wouldn't run into any significant difficulties.
The designers took the plunge. Four enormous pods hang under the hull like giant outboard motors. Each of these units weighs as much as a fully loaded Boeing 747. Unlike cruise ships, which are fitted with just 2, the QM2 would be fitted with an unprecedented 4 pods, and they're the largest ever built. The rear pair would be able to swivel 360 degrees, pushing the boat in any direction, so there's no need for a rudder. At the front of the ship, 3 huge propellers called bow thrusters would be set in the hull behind swivel doors. Together, the pods and thrusters would give the world's biggest liner exceptional maneuverability in tight situations.
We can turn this ship around on a pinhead. It's just incredible.
But when the time came for the radical propulsion pods to be fitted, trouble hit. Similar pods fitted to 4 other cruise ships failed consecutively. The thrust generated by the propellers transfers to the ship through metal bearings, which were wearing down under the immense pressure. Unable to leave port, the afflicted holiday ships were confined to dock. Multi-million-dollar cruises were cancelled.
It's a very difficult thing when you've got a ship under construction and suddenly you hear that one of the key components of the ship may potentially be a source of problem.
These technical difficulties delayed the pod's delivery. The schedule was thrown into turmoil. Soon the ship should have motored out of the construction dock and into a larger dock to begin the fit-out, powered by her new pods. But without a propulsion system, the QM2 was paralysed. What should have been a glorious moment, the first time the QM2 moved under her own steam, was about to go wrong. The appointed day arrived, March 21st, 2003, and the pods were still nowhere to be seen. But the construction team could wait no longer to get her into the new dock. At 4 a.m., under cover of darkness away from the glare of the world's media, the Queen Mary 2 moved out into the river, but she was being pulled by tugboats. Her lack of pods made the transfer more dangerous and delayed the schedule. The shipyard still didn't know when they'd be delivered. Construction workers could finally begin phase 2 of the project, the fitting out of the QM2. This task was enormous. Not only was she the largest passenger ship in the world, but the work had to be done in record time. In just 8 months, the plumbers, electricians and engineers had to fit 1,500 miles of electric cable, 300 miles of ducts, mains and pipes, 9,000 loudspeakers and 80,000 lighting points. 3,000 fitters had to install 1,300 cabins, a nightclub, ballroom, casino and theatre, art galleries the largest library afloat, 5 swimming pools, a basketball court, and, to top it all, a full-scale planetarium. There was no room for error. Any delays now would push the shipyard team over the crucial delivery date, at a cost of £300,000 a day.
Probably the delivery of the ship.
The biggest threat to the deadline was the crisis-ridden pod propulsion system. Finally, after extensive testing and just 6 months before delivery, the new improved pods arrived.
People were hugely relieved because the faults were mended.
The pods were assembled and fitted to the base of the ship. With their own means of propulsion, the QM2 had turned from a steel shell into a functional ship. With the pods taken care of, the QM2 approached her final hurdle: the sea trials. On September 25, 2003, there was cause for celebration as the Queen Mary II sailed out of the dock under her own power for the first time.
The excitement on board the ship and within the town of San Jose when this ship moved for the first time under her own power was absolutely unbelievable.
For the next 3 days, 40 separate tests were carried out. She had to pass them all. Anchors were dropped and retrieved. The ship performed crash turns, and the rescue boats were deployed. Everything was going to plan. To test the ship's maneuverability, the underwater bow thruster doors opened and they were turned to full throttle. But something wasn't right.
One of the bow thruster doors inadvertently closed when the thruster was running and the door was blown off.
The heavy steel door sank rapidly to the ocean floor, leaving a tear in the ship's hull. It was completely unexpected, only 3 months before the deadline. The Queen Mary II limped back to the shipyard. The efficiency of the ship's movement through water would be seriously affected.
With one of the doors missing, it would mean that there would be a lot of turbulence, which would slow the ship down.
The speed trials were in just 4 weeks, but the suppliers couldn't make a new bow door in time. The shipyard had no choice but to try to make this specialist piece of technology themselves. As the engineers worried about the bow door, the decorators also had a huge task ahead of them. 250,000 meters of flooring and carpet and works of art worth £4 million had to fill vast public rooms and endless corridors. The hull needed 200,000 litres of red and black paint, but the QM2 had to also be thoroughly green, so the paint is non-toxic to marine life. With just 3 months until delivery, they couldn't afford any setbacks. After a month of feverish activity, the decorators were well on course to finish by the delivery date, and the engineers completed the bow door just in time for the speed trials. The QM2 was beginning to look like a magnificent ocean liner as she took to sea again. The designers had specified that the ship must be capable of a speed of 29.35 knots to cross the Atlantic on time, an ambitious target for such a large ship. The QM2 was tracked by satellite as she made runs of exactly 1 mile. On the final run, the helmsman from the shipyard handed control of the ship to Commodore Warwick. As he took control of the ship for the first time, he turned the engines to full throttle. The speed hit a peak of over 30 knots. With an average of 29.62 knots, she is significantly faster than specified in the contract. Everyone was delighted.
She'd actually performed far better than we had ever expected.
To reward the ship workers for their excellent work, Cunard and the shipyard planned an open day. On November 15, 2003, the proud workers showed off the ship to their families. Hundreds of visitors streamed on and off the liner to see the luxurious rooms inside. But then, disaster struck. A gangway above the dry dock collapsed. 16 people plunged to their deaths on the concrete floor 20 meters below. 30 more were seriously injured.
Tragedy of that event was definitely the low point.
The shipyard workers were determined to finish construction on time, despite the tragic collapse of the QM2's gangway. The crucial final touches had to be carefully put in place before she'd be accepted by Cunard. Against all the odds, after a month's hard work, the QM2 was finally ready for delivery, on the very day that had been specified 2 years before. On Boxing Day 2003, the completed Queen Mary 2 left Saint-Nazaire and was delivered to owner Mickey Arison.
It was a euphoric day. I felt that we'd really accomplished something very, very special.
Queen Elizabeth II agreed to name her in a spectacular ceremony.
May God bless her and all who sail in her.
The Queen Mary 2 was born. And there has never been a ship like her. Everything about her is on the largest scale.
It's her strength, her speed, the majesty of the ship itself, and people feel that when they're aboard.
She has the biggest ballroom afloat, a theatre, the world's only floating planetarium, and the magnificent Britannia dining room. Mickey Arison and Stephen Payne have achieved their dream of creating an ocean liner for the 21st century.
The ship now exists, and it's proving all those people who said there would never be another transatlantic liner absolutely wrong, because the ship is here and she's doing very well.
The QM2 has taken over the historic transatlantic route from the QE2. Now, after 5 days at sea, she's a day away from New York and has entered thick fog. Commodore Warwick is responsible for the lives of nearly 4,000 passengers and crew. Larger dots on the screen represent objects picked up by radar and could be ships, icebergs, or even whales. One of these dots is moving towards the QM2 on a potential collision course.
We've now identified the ship approaching us. On the radar is indicating that she's travelling at 4.3 knots.
The state-of-the-art computer works out the ship's route and calculates that they will pass too close for comfort. Warwick takes averting action.
We've made a broad alteration of course to starboard so that we'll pass well clear of each other.
The QM2 is safely on track. But down in the galley, staff are preparing for the next challenge: dinner. At one sitting, 1,100 passengers eat their silver service gourmet meal. Within 30 minutes of diners finishing, the kitchen and waiting staff turn it all around and are ready to serve the next 1,100. Early the next morning, they finally arrive at the port of New York. This is one of the most testing parts of the voyage. The Hudson River has strong currents that can make docking incredibly hard. All the ship's innovative design elements must work together under the masterful eye of the captain. The satellite system calculates the QM2's exact position relative to the pier, so that the powerful pods and bow thrusters can maneuver precisely into the narrow strip.
20 metres off, maintaining, thank you.
Starboard pod, down to 4.
3 on each pod.
3 on each pod.
Even a slight breeze could blow the ship against the side of the berth, damaging her and destroying a pier.
When we get off the dock, we then have to take a right angle turn to go into a fairly narrow slip. So this is quite a critical maneuver, and we have to be prepared to use a lot of power on our podded propulsion.
Commodore Warwick guides the vast ship perfectly into the berth.
Stop the azimuth pods.
Thank you,
Okay, that's it, guys.
Once she's docked in New York, the QM2 has just 10 hours to load up, turn around and be ready to do it all over again.